This is video 9 of the GCSE Physics video series, all about motion. And it's only a short video, I hope, this time, because this chapter has only got 4 lessons in it. So here is lesson 56. Lesson 56, about speed and distance time graphs. Now, very often these are covered in Key Stage 3, so I suspect you've probably done these already, and this will be a nice short section, but we'll see. Let's start with some equations. The equation for speed, or what we should say average speed, is the total distance that is travelled divided by the duration of motion, how long it takes to travel that distance. Now, this is interesting. We use an S for distance, and we use a V for speed. We never use an S for speed. Now, I have seen resources and notes and videos online and such where they write S equals d over t, and the students can think, okay, I understand that. S is speed, d is distance, and so on. But be careful, because you will be given equations, not all of them, but there are equations that you will be given in your GCSE. And they will never, ever use S for speed. They will always use V for speed. And you'll be given an equation, which we will cover in this video series a bit later, but you will be given an equation, v squared equals u squared plus 2as. That's an equation that you need to be able to use. And in that equation, v means the same thing as it means here, and s means the same thing as it means here. So getting in the habit of using these symbols that all physicists agree to use is a good idea. S is distance, or if it's in bold as we write it, displacement. We use S for distance and S for displacement. And the reason why it's an S is because the Latin word spatium. Don't know if I'm pronouncing that right or not, because I don't speak Latin. V, average speed, velocitatum, and T, time, from tempus. So that's where these words come from. So don't use an S for speed. It's a sloppy habit to get into. It's a shortcut to make you feel like you're getting something right early on, but it causes problems further down the line. Better to get it right first time than to have to unlearn something that you've learnt incorrectly. So here we go. We've got the title as Speed and Distance hyphen time graphs. Now, by convention, if we are referring to something as a something graph, the first something is what goes on the y-axis, and the second something is what goes on the x-axis. So this is just saying speed time graphs and distance time graphs. Speed hyphen time graphs and distance hyphen time graphs. It's all just a bit compressed down into a smaller space. So a speed time graph has speed on the y-axis, time on the x-axis. A distance time graph has distance on the y-axis, time on the x-axis. That's what we mean by that. On a distance time graph, the gradient of a line represents a speed. That's what it is, because it is a difference in distance, so it's how far has been travelled, divided by a difference in time, an interval of duration, how long it has taken to travel that distance. And just because the equation for speed is distance, or average speed is distance divided by time, then the gradient of a distance versus time graph is the average speed. That is what it is. Now, when we measure a gradient, we do need to be quite careful. When we learn gradients in mathematics, we might draw piddly little triangles and count the number of squares vertically and count the number of squares horizontally, and then do the number of squares vertically divided by the number of squares horizontally, and then say, ah, yes, that's the gradient. But of course, that's because mathematicians do not place as much importance on units and what the dimensionality of the quantity is, whereas we do. As physicists, we think it's very important indeed. This graph is representing a physical situation. It is not a pure mathematical abstract. It is an abstraction. This is a pictorial pictorial representation of reality. That's the big difference between maths and physics, or one of the big differences. So rather than doing a piddly little triangle and then trying to count how many little squares, that's a bad idea. What is better is to project from two places along the line. Here I happen to have drawn an X on those two places. But just be aware, these X's, these don't represent data points. When you draw a distance time graph or a speed time graph, data points, which we usually use an X for, are used to draw the best fit line, which, again, another difference between mathematics and physics. A best fit line can be curved in physics and it would still count as a line. Whereas in mathematics, they would say that a curve is a curve and a line is always straight. Well, according to Euclid, a straight line is the shortest line connecting 2 points. And if those shortest line connecting those 2 points follows a curved path, that's still straight. So it's just it's just a fun little thing for you to argue with the maths teacher about. When we say a line in physics, it could be straight, it could be curved. They're both lines. It is a difference in terminology between subjects. Get used to it. That is something that happens quite a lot. So the X's here don't represent the data points that have been used to draw the best fit line. I haven't bothered doing those data points. These X's just represent 2 points along the line that are as far away from each other as possible. Not data points, just places along the line. Don't use data points for this. So once you've got your line, you can ignore the data points. I actually prefer to use little circles or dots to indicate the places on the line where I'm taking my gradient. They want to be as far apart as possible. At A level, we say at least 8 centimetres vertically apart and 8 centimetres horizontally apart. In GCSE level, often the graphs are a bit too small to make that work, so just make them as far apart as is practicable. And then, rather than doing a triangle, what I find is better is to measure the numbers off the axes, not counting squares, which means getting my ruler out and very carefully projecting horizontally back to the y-axis. And if necessary, doing so for the bottom part as well. And vertically projecting, following those lines and trying to draw as straight as you can. If the ruler's a bit wonky, you end up with bad data. And then reading off the y-axis and reading off the x-axis. And I would even write on the y-axis and on the x-axis, or near the y-axis and near the x-axis, like I have here in blue and red, I would even write the numbers that I am using. So final value subtract initial value, that is 11, that is 3, 11 subtract 3 is 8. On the y-axis, 9 subtract 0. I would write 9 subtract 0. I wouldn't just write 9. I would even possibly write the points around here and here. And you'll often see me as well actually writing them as coordinates on here. So I'll put in brackets, this is 9, 11. And this one down here is 0, 3. I'll even write on those places on the line coordinates. Now that does two things. Firstly, it reminds me of what the values are I am using, so I don't just start counting squares. But secondly, it shows the examiner the values you are using. Write it on the graph, because when the examiner is marking questions where you have to calculate a speed from a distance time graph, they will look at the graph and be looking for evidence that you have done a gradient calculation. This is all pretty good evidence that you've done a gradient calculation, what is shown on this graph here. Annotate the graph when doing the calculation. It is critical. Use as big a range as you can get away with. The steeper the line, so the higher the gradient, the higher the speed. Fine. You can't get a negative gradient on a distance time graph. Not technically. Why is that? Because distance can never reduce over time. We talked about that in the last video. Difference in definition between distance and displacement, and a difference in definition between distance to a physicist and distance colloquially. Same word, different meanings. However, I have seen questions, particularly in textbooks to be fair, but I have seen questions where it says distance on the y-axis and the line shows a negative gradient. That is just the person who made the question being a bit confused, a bit lazy, a bit cluttered, and it's not correct. Okay, so just be careful with that. Moving on to the next lesson. So this was distance time graphs. I haven't even mentioned speed time graphs, but if we had a speed time graph, how would we analyze it? Well, I'm going to jump to velocity time graphs. The principle is the same, except you're going to get a scalar out of your graph rather than a vector out of your graph. So let's look at velocity time graphs. And then when we look at speed time graphs, it's the same idea, the same physics, but because speed is a scalar, from the graph we can only extract scalars. So this is lesson 57, velocity and acceleration. Some more equations for you. Acceleration is the rate of change of velocity. So that means the change in velocity divided by time. The change in velocity is the final velocity, v, subtract the initial velocity. So u is initial velocity in this equation. And then divided by the duration of motion, t, time. Sometimes you'll see it written with a triangle called delta, the Greek letter delta v, to mean the change in velocity. So this might be delta v over t. Sometimes people write delta v over delta t. That's not actually quite correct. I have seen that a few times, and the reason why that is done is because it's a stepping stone into A-level mathematics and A-level physics, where we start looking at calculus and we start looking at infinitesimally small changes. But really, if we have defined t as a duration of motion, an interval along the time axis, we don't need the delta because of how we defined the t. So delta v over t, or v minus u over t, means the same thing. Often the equation is given like this instead, or it might even be given as v equals u plus at, which is of course the same equation. I've just written it here a few different ways. So speed, scalar, velocity is a vector. Just a reminder for you there. Acceleration, which is rate of change of velocity, has to have a direction. And the direction will be the direction of the change of velocity. That is the direction of the acceleration. So if our final velocity is higher than our initial velocity, then we are going to end up with a positive change in velocity. Call that forwards. If our final velocity is less than our initial velocity, we're going to end up with a negative change in velocity. Call that backwards. So if we have a negative change in velocity, we have a negative acceleration. If we have a positive change in velocity, we have a positive acceleration. Now, we're just considering here direction along a line, and that's about as complicated as it gets at GCSE level. When you do move on to A level, we will be looking at 2- and 3-dimensional acceleration vectors. But for now, 1-dimensional acceleration vector, we've got forward is positive, backwards is negative, that's fine. We don't need to go too complicated. We tend to just use displacements in terms of we tend to just use vectors in terms of displacements and forces at GCSE level, maybe velocities, but not accelerations. We're not going to be resolving accelerations, I don't think. Probably not. I've never seen it before at GCSE level anyway. But acceleration is a vector. Displacement's a vector. Displacement is the distance travelled in a particular direction. So this is just a reminder of stuff we've kind of seen before. So let's look at this graph now. Let's zoom in on this graph for a second. This graph shows velocity versus time. And you can see that the velocity can go down. Speed can go down as well. This is not like distance that can't go down. You can increase speed, you can decrease speed. But speed can never be negative. So if you see it says speed versus time and the graph goes negative, then whoever made the question has been a bit sloppy. Velocity can be negative. You can have a backwards velocity. But speed can't be negative. So this is velocity versus time. So we've got velocity on the y-axis, and here we have a negative gradient. So positive velocity, 10 meters per second down to 5 meters per second. Section A of this graph, this line here, has a negative gradient. Now, we had defined, let's just grab my page and move up here. We had defined our acceleration as the change in velocity divided by that interval in time, that change, that duration of motion. So that our acceleration is a difference in the y-axis divided by a difference in the x-axis. That is a gradient. So our acceleration is represented by the gradient. So you can see here that we have a very steep and negative line. So the gradient of this line is the acceleration. Because we have positive velocity and yet the speed is reducing over time, that acceleration we could call a deceleration. Let's be a little bit careful, because deceleration is technically a scalar. It's the rate of decrease of speed. You can never have a negative deceleration. That wouldn't make any sense. So here we're talking about deceleration, and that could get a bit confusing because deceleration is not a vector. Doesn't matter. This is a negative acceleration, and we can calculate what it is. So if I got out my gradient calculation, get out this to do a gradient calculation, this point over here has the values 0, 10. This point down here has the values 1, 5. Difference in the y-axis is the final value, subtract the initial value. Difference in the x-axis is the final value, subtract the initial value. So that is -5 divided by 1, or -5. And now we need to look at units. It's meters per second divided by seconds, meters per second, or meters per second squared. So -5 meters per square second. That is what I would do for a gradient calculation in that first leg of that journey. Second leg of the journey, we're accelerating, we're getting faster, so it's a positive acceleration with positive velocities. Fine. The acceleration magnitude isn't as great in part B as it is in part A, but we could calculate the acceleration there. And in part C, we could calculate it as well. So that's how we relate the idea of velocity to acceleration. But what about deceleration and trying to understand deceleration? Well, I've got a handy little table here which might help. So it is not always true that negative acceleration is deceleration. That is not always true. So I've got 4 cases here. The first 2 cases are we are having our velocity vectors pointing forwards. So at the time we're calculating the acceleration, we are moving forwards. The second 2 cases, at the time we are calculating the acceleration, we're moving backwards. Our velocity is backwards. And then we have the first and third case, we're accelerating forwards, and the second and fourth case, we're accelerating backwards. So you can see we've got every possible combination. Velocity forwards, so we're moving forwards and we're accelerating forwards. Velocity forwards, so we're moving forwards but we're accelerating backwards. Velocity backwards, so we're moving backwards but we're accelerating forwards. And velocity backwards, so we're moving backwards and we're accelerating backwards. Now, if we are moving forwards and we are accelerating forwards, then we're going to get faster. So we have a positive velocity. We have a positive acceleration. We've decided forwards is positive, backwards is negative. So that's not deceleration. Our speed is increasing. If we're moving forwards and we're accelerating backwards, so we've got a positive velocity forwards, negative acceleration backwards, and we are going to be slowing down. Because our rate of change of velocity is in the opposite direction to our velocity, we are going to be reducing velocity over time. We're going to be getting slower. So this is what people usually think of, those first 2 cases where they say, oh, deceleration is negative acceleration. But let's have a look at the next 2. Let's have a look at number 3 and number 4. So number 3, the velocity is backwards and the acceleration is forwards. And the velocity is backwards, so it's negative, but our acceleration is forwards, so it's positive. Well, in that case, if our velocity is initially negative, but we've got a positive acceleration, our velocity magnitude is decreasing. We're slowing down. So as we're slowing down, we are decelerating. So our velocity is backwards, but our acceleration is forwards. We are slowing down. We are decelerating despite having a positive acceleration. And in the last example, our velocity is backwards, but our acceleration is backwards. So we're moving backwards, we've got negative velocity, and we're getting faster because we've got a negative acceleration. So this is a negative acceleration, which is not deceleration. So can you see, we've got one negative acceleration that is deceleration, one negative acceleration that's not, one positive acceleration that's not, one positive acceleration that is. So you can't just say negative acceleration is deceleration. It's not true. Deceleration, however, is a scalar. Now here's a way of thinking about deceleration. Let's get the pen out. Here's a way to think about it. If I have an acceleration of 1 meter per second squared, what that is saying is every second my velocity changes by 1 meter per second, and that's a positive 1 meter per second. So if my velocity was initially 1 meter per second, positive 1 meter per second, then after 1 second, let's have each of these examples where the time equals 1 second, my new velocity will be 2 meters per second. I have gained 1 meter per second of motion, so that's 1 second. So per second I've gained 1 meter per second, so I've gone from 1 to 2. So that is our positive acceleration, positive initial velocity, and our final velocity is faster. We are getting faster. Now let's look at the second case. So let's erase all ink. Let's say that my initial velocity, let's say 10 meters per second. So it's positive because we're moving forwards. But our acceleration, let's say it's negative 1 meter per second squared. Say negative, we're accelerating backwards. Duration of movement, let's say 1 second. So what's our new velocity? Well, it was 10 meters per second. It's now going to be 10 plus negative 1. We are gaining negative 1 meters per second of velocity per second. So if we gain negative 1 meters per second of velocity every second, and we've been moving for 1 second, then we've gone from 10 to 10 plus negative 1, which is 9 meters per second. So that's your example of, let's draw a little plus in there, still positive. So that is our example of negative acceleration causing deceleration. Our speed has reduced. Now let's look at the third case. In the third case, our initial velocity is backwards, negative 10 meters per second. Our acceleration is forwards, that's positive 1 meter per second. And let's keep our duration as 1 second, just so we get a feel for what's going on. So what's happening with the final velocity? Well, we have been gaining positive 1 meter per second, that should be squared, every second. Gaining positive 1 meter per second. So we've gone from negative 10 to negative 10 plus positive 1, which is negative 9 meters per second. And now look, the speed has reduced. We were going at 10 meters per second backwards. We're now going 9 meters per second backwards 1 second later. So that is a positive acceleration causing me to slow down. And if we slow down, then we are decelerating. So that is a deceleration with a positive acceleration. And the final case, our initial velocity is backwards, 10 meters per second. Our acceleration is backwards, negative 1 meter per second squared. And let's have 1 second. And you can see how this is working now. If our initial velocity is negative 10, we add our acceleration on every second. So negative 1 meter per second for 1 second means I'm adding negative 1 meters per second to my velocity. So negative 10 plus negative 1 is negative 11 meters per second. So I have a negative acceleration, but I have got faster. Yes, I'm moving backwards, but I'm still going faster after the acceleration. So negative acceleration, but definitely not deceleration. I'm getting faster. So I'm hoping that's cleared up those 4 examples. I spent quite a few minutes on it, but I'm hoping that's cleared up what's going on with this table here. It is important that you've got a clear idea in your head of the difference between acceleration and deceleration and what it all means. So, velocity and acceleration, done. Let's move on to lesson 58. Lesson 58, we focus a bit more on our velocity time graphs. So here I have my velocity time graph, and as before, I can calculate the acceleration from this graph by calculating the gradient. But I can also calculate the displacement of this motion that's represented by this graph. And I could do that by using the area between the line, the data line, and the x-axis. And you do need to memorize this. On a velocity time graph, gradient is acceleration, area is displacement. On a speed time graph, gradient is the magnitude of acceleration, and area is the distance. Not to be confused with on a displacement time graph, where the gradient was velocity and the area had no physical significance at all. Or on a distance time graph, where the gradient was speed and the area had no physical significance at all. So the area here is the displacement. Okay. So the gradient is 0, we've got constant velocity. It doesn't mean we're stopped. This is a very common mistake. Students will see a straight horizontal line and they'll think, the acceleration is constant. Or they'll say, we've stopped. Neither of those is true. It just means our velocity is constant, so the acceleration is 0. So I suppose technically we do have a constant acceleration, but a constant acceleration of 0. We're moving at a constant velocity. Constant velocity, which means constant speed in a particular direction. It is possible to have a constant speed that is not a constant velocity. If we're moving in a circle, for example, perhaps we're going around a roundabout at a constant speed, but our direction keeps changing because we're going in a circle. Well, our velocity is speed in a direction, so if our direction is constantly changing, we have a changing velocity. Therefore, we're accelerating. So we can have a constant speed whilst we're accelerating if we're going in a circle. We're accelerating towards the centre of the circle. Circular motion comes up when we talk about space in video 16, so I won't talk about too much more about that at the moment. So, okay, area. Why is the area here the displacement? Well, let's just take a little square and we'll understand why. If we just look at a little square of this, the area represents 1 metre per second multiplied by 1 second. Well, just have a look at the units. 1 metre per second multiplied by 1 second. The seconds cancel, and you're left with 1 metres. We could do an area like this, which is 5 multiplied by 1. In that case, you've got 5 metres per second multiplied by 1 second is 5 metres. Or we could look at an area like this, 6 multiplied by 3. So we could go 6 metres per second multiplied by 3 seconds. So that's going to be 18 metres. I really hope I've got my times tables right there. So you can see that the area is a value on the y-axis multiplied by a value on the x-axis. Now, if you've got a nice regular shape, you can calculate the area. So you can break the shape into easier shapes, rectangles and triangles. The area of a triangle is half times base times height. The area of a rectangle is just base times height. And you can compute the area, multiply these values to get the area of each shape and then add those shapes together. So with this yellow one here, we've got a rectangle, which is 8 seconds multiplied by 7 metres per second. That is this rectangle here. Oops, slightly curvy line. That rectangle there. And then we've got a triangle on the top, which is 3 multiplied by 8. So half times base times height, half times 8 times 3 gives us 12 metres. 56 times 12, 56 add 12, sorry. Adding the two areas together, you get a total displacement of 68 metres. Now, you can do that if you've got nice shapes. If you've got a curve, then you can't. What you can do then is, below where the curve is, you can break it down into simple shapes, sure. But along the curve, you've got to count the squares. And the rules are, when calculating an area by counting the squares, you count the whole squares we've got, So, I mean, this is 25 here, so I'm not going to bother counting them. This is 15 here, so I'm not going to bother counting them. Let's just take this little bit here. We count the whole squares. 1, 2, 3, 4, 5, 6. That's all the whole squares in this little bit here. Then you count the part squares, and any part square counts as a half square. So that is 1, 2, 3, 4. So that's 4. Look, 1, 2, 3, 4. That's 4 part squares. And what I would do is I'd say a half and 1 and 1.5 and 2. So I'd say that is 2 in half squares, or I'd put 4 times a half to get 2. These numbers here are for the whole shape. So there are 63 whole squares here. And then there are 10, if we count along the edge, part squares. Let's just check and see if this was right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, 10 part squares. Each part square is half a square. So 63 plus 5, which is 68 squares in total. But how much displacement is represented by a square? Now be careful with this. In this example, for simplicity, 1 square is a velocity of 1 for a... Why have I done a v there? A velocity of 1, let's cross that out, for a time of 1. That's 1 meter per second for 1 second, 1 meter. But if the numbers on your axes are different, then the number of squares, just the number, the raw number, will not be a displacement. You will have to multiply it by the displacement per square. Number of squares multiplied by displacement per square would give you the displacement, with the units, which depends on the axes. So that is how we can calculate the area under a velocity time graph, which represents the displacement. You won't get a situation where you've got negative values on the y-axis and you're counting areas. If you do, well, then area is then negative, which means that we are being displaced backwards. And if you've got a total displacement and part is positive and part is negative, then you add the two together. You could even end up with a displacement of 0 if you've gone somewhere and back to where you started. A classic example of that is when you look at the motion of a ball bouncing, and then the velocity time graph, while it's in free fall, whether it's ascending or descending, because the acceleration is 9.8 meters per second, or 10 meters per second if you're doing one of the other exam boards, then you're going to get a diagonal straight line while the ball is ascending and descending. Every time it bounces, of course, the velocity suddenly changes from being downwards, call it negative, to upwards, call it positive. So the graph, you get this sort of diagonal line that crosses through 0 on the y-axis, then shoots up again, and then does it again, and shoots up again. And that's a very common question that comes up. Finally, what do we do with curves? When we're analysing motion graphs, what do we do? So I've left the axes clear here of anything written down. If the first thing you want to do is check the axes, what's being plotted. So this could be displacement. If this is displacement, I'm going to use an S for this in meters, and this is a time in seconds. Then we know the gradient is going to be a velocity, and the area has no physical significance. If it is a velocity versus time, then we know the gradient is an acceleration, and the area is the displacement. So distance versus time, gradient is speed, area has no significance. If it's a speed versus time, gradient is the magnitude of acceleration, area is the distance. So you know this stuff, and that's listed here on point number 3. So check the axes, check the scales. So here, each little square is not 1 by 1 anymore. So if we're doing areas, we need to be careful. If we count squares to calculate areas, then each of these little squares is 100 in the vertical direction, multiplied by, how many is it? 5. Oh my goodness me. 20 divided by 5 is 4, isn't it? So 4. So each of these represents 400 meters, each little square. If this was a velocity time graph, which would be in meters per second, then each of these little squares represents 400 meters of displacement, and then you would, do your counting squares thing because we've got curves here. If you are computing gradients, so that could be because you need a velocity from a displacement time graph, or it could be because you need an acceleration from a velocity time graph. If you're calculating gradients, but the line is curved, then I would first of all put a mark on the line at a time that you are asked to calculate the gradient. So let's say this is a displacement versus time, and we are asked for I'm not going to bother writing the units, and we are asked, I can't not. And we are asked for the velocity at 84 seconds. And I'm going to start by putting a mark on the curve at 84 seconds. I'm then going to take my ruler and I'm going to position it so that I can draw a tangent, a line that touches the curve at just one point. And I'm going to draw my tangent as carefully as I can at that point. That's what this red line here is. When drawing a tangent, it's a good idea to look a few centimetres to either side of the data point, of the point, and check that your tangent is about the same distance away from the curve. It's a skill that you acquire over time. A 30 centimetre clear plastic ruler is absolutely essential for this. But get lots of practice in. And then finally, you're going to calculate your gradient. So you could use this point here, and maybe let's find another sensible one. That one looks like it goes right in between the grid lines there. So then I'm going to label this point up here. That is 80, well, it's 4 less than 100, so that's 96 seconds, and it's 100, so 2600 on the y-axis. And then this point down here, it looks like it's exactly halfway. Anyway, that's 60 on the x-axis. On the y-axis, it looks like it's 150. And then I'll do my gradient calculation, which is the difference in the x-axis, 2600 subtract 100 and y-axis, 2600 subtract 150 divided by the difference in the x-axis, which was 96 subtract 60. There we go. And I'll chuck that into my calculator. I've got a calculator to hand, so I won't do it now. You chuck that into your calculator. That would give you your gradient. And then finally check units. Meters per second. So this is why it's so important. If I had a ruler, I'd draw these lines across to the axes so that I could read these numbers off carefully. And that's it for motion graphs. On the bottom right here, you've got some equations. So you've got our definition of an average. This is a mean average, which is adding all the velocities we've got and dividing by how many we've got. Well, we've met two different symbols for velocities so far. Let's just go back a slide to lesson 58. Last lesson we had v, which was final velocity, and u, which was initial velocity. Or we could go back to lesson number 57, where I introduced u as initial velocity, v as final velocity. So using that same convention, final velocity plus initial velocity divided by 2 is our average velocity. Now that only works if we have a straight line on a velocity time graph. In other words, if our acceleration is constant, that's the only time this works. Now, our displacement was our average velocity multiplied by time, so you could write it like this. And if we wanted to, we could rearrange the equation here, v plus u over 2 times t. We could rearrange that, but we'll leave it like that for now. The acceleration equation was acceleration equals difference in velocity divided by time. So that was a equals v minus u over t. We met that in, well, I think we met it the lesson before as well, didn't we? Yeah, we met that in lesson 57. So here we are in lesson 59, rearranging velocity minus final velocity minus initial velocity over time equals acceleration. By multiplying through by time and dividing through by acceleration, our time is this. So we now have these two equations here. Now what we could do is we could substitute this into this equation here. So displacement is equal to v plus u over 2 times t. I could substitute this into there, and I end up with displacement equals v plus u over 2, that's this one, times, instead of t, v minus u over a. I hope I've said all this bit right. I think so. If I've messed up, my apologies, but it should be enough that you can follow here. Then what am I going to do? Well, I mean, I could put brackets around these bits here so you don't get confused. That's what I might do if I was teaching it in class, is I'd chuck some brackets here so you could see these bits there separately. But what I would say is let's multiply through by 2, multiply through by a, and you end up with 2as equals this. And if you multiply out these brackets, you end up with the difference of 2 squares. So v squared equals u squared plus 2as, which is just a rearrangement of this equation at the bottom. You do need to be able to use that equation. So you need to be able to algebraically manipulate that equation to get u, v, a, or s as the subject. So don't forget, if something is squared, the inverse function is a square root. That's it. That's it for this video 9, all about motion. Let's just switch back so you can see my full face or something. Right, so next video is going to be video 10, which is, I don't know what that's about. Video 10, force and motion. So we've had forces in balance, we've had motion, now we're going to have forces and motion. So a lot of very similar topics coming together, but it's got lots of momentum and stuff like that in it. Hopefully you found that helpful. It was pretty quick, but you can always watch parts of the video again. And if you do want extra help with that, well, do sign up to the weekly tuition sessions. But I'm not going to advertise them again. I've done it plenty of times. So take care of yourselves, and I'll see you next time.